Welcome back, students. Today we are going to see the chapter threads. We'll be seeing the overview, multi-threading model, and threading issues. Most modern operating systems and applications are multi-threaded. Threads run within the application. So what do you mean by this? In the last chapter, we have seen that the process is a program in execution. There, the process was considered as a single thread. That means when a process starts its execution, it has a single task being done at a time. But in threads, we have multiple tasks being done by a process simultaneously. So multiple tasks can be done by threads simultaneously. Like for example, you can have updating of display, fetching of data, then answering a network connection or spell check. All these are done by the single application but by different threads simultaneously. So all these activities will take place simultaneously. For example, a word processor. A word processor has multiple tasks to do simultaneously. Like here we are saying this update the display. So when you are typing a document in a word processor, that word processor is reading the text that you are entering into that document. Apart from that, it is also simultaneously updating the display to give it the formatting that you want it to have. It also does the spell checking, and it also is sometimes checking the internet for any formats or diagrams that you would like to add to it if you have made a request for it. So this is how a process will be doing multiple things simultaneously when it is a multi-threaded application. Now we have seen process and now we are seeing threads. Process is when a process is created, it is created by allocating a lot of resources. That's why we say that process creation is a heavyweight process, while as a thread creation is a lightweight process. What is the difference between heavyweight process and lightweight process? Heavyweight process means when a program is asked to execute, its execution begins, a lot of resources are allocated to a process. And when a thread is started for execution, is created for any task to complete within the process, then it is not allocated any new resource. The resources that are allocated already to the process, the same resources are shared by all the threads of that process. Threads simplify code and also increase efficiency. Most of the modern operating systems are also multi-threaded. So kernels are multi-threaded means nothing but operating systems. The core process is also multi. So how do you define a thread? A thread is defined as a basic unit of CPU. Has or it comprises a thread ID, a program counter, a register set, and a stack. Now we already know that for a process, a program counter will be there that indicates which instruction has to be executed and all that. We also have register set to store the data. We have stack to store the local data and the function calls. Along with all these, thread has an additional information, that is the thread ID. Now these informations are specific for a thread, where other data with other threads like the code, data and files. In this diagram, you'll see figure A represents a single threaded process and figure B represents a multi-threaded process. Figure A has a single thread of execution. It's a process, a normal process, whereas in figure B, we have multi-threaded process. It means that one process is doing 3 tasks simultaneously. Now you can see there are 3 threads in figure B. So it indicates that 3 tasks are being done by this figure B. Now I said that register, stack and thread ID are specific for each thread. So this is here you see that registers and stacks are dedicated for each thread. So each thread is having this information. This data is exclusively for the thread. Whereas if you see that the code, the data and files of a process are shared between all the three threads. So this is how threads have some data which are dedicated for each of them and some data that are shared between all the threads. So if a process is a single threaded, then the task completion takes more time, whereas if a process is multi-threaded, then multiple tasks are running simultaneously, hence it takes lesser time for the same task to complete. Take for example a word processor. If you had single threaded word processors, then you would have to type first, then finish all the typing of the document, and then you would have to go in and format that text. After formatting the text, probably you would go for checking its grammar and spellings. But nowadays, word processors are such that they automatically change the spelling as you type. If you are having a typographic error, it fixes itself. That's how it is multi-programming, multi-threading. So multi-threading means there is text being read and simultaneously it is also checking the spelling. So there's one thread which is taking the input, another thread which is checking the spelling, third thread which is doing the formatting. So that is what is multi-thread. Next, let's also understand web servers. Here's another example of a web server. These web servers are also multi-threaded now. So every time a client makes a request to the server creates a thread for the new request and it makes this new thread answer the queries of the client and send the data back to the client. So this is how a multi-threaded web server works. It every time a new request comes, it creates a new thread and it itself waits for the incoming client's request. So this way a web server can serve multiple requests simultaneously. That's how our web servers are working to reply or to service so many clients simultaneously. Thousands of clients are requesting for different data like web pages. It may be web pages, it may be images, it may be sound, video, and so on. So a web server not only handles multiple clients, but it also handles multiple types of requests. Next, we see the benefits of threads. Threads are responsive. What do you mean by responsive? Nowadays, you'll have seen the web pages. The web page is partly downloaded and still you're able to see and move around the pages. So first it downloads the text because there is a thread that is downloading the text. Downloading plain text takes lesser time as compared to downloading the images because an image cannot be loaded on the screen until unless it is not fully downloaded. Hence, the web servers now work in sending different contents of a page through different threads. So the browsers download the image with a separate thread and the text through a separate thread. So text gets downloaded early and hence it is displayed while the images are uploaded or the images are displayed later as and how they get downloaded. So that is how your page is more responsive. So even when the page is not completely downloaded, you get to read the contents of that web page. So how this works? This can also be in terms of applications also. If your application may be multi-threaded, if one of the thread is blocked, it calls the system blocking call, then also the other threads are actively working and hence it provides more responsiveness. Next is resource sharing. Now threads do not have dedicated resources allocated to it. That's why they share the resources that are allocated to the process. So if the process is having 5 threads, all 5 threads are sharing the resources. In this way, there is efficient use of the resources like memory and message passing. All these are shared between different threads. Next is economy. Creating threads is cheaper than creating the process. Creating a new process requires a lot of resources allocated to a process. So operating system has to allocate it memory, it has to be brought into the main memory, then it has to be given to the CPU for execution. So this is a little costlier affair as considered to a thread, because a process is already created and is in place and it is having space in memory. Creating a new thread will only create a new thread within that same memory location, and hence the code also is getting executed from the same space. So it is economy. So it provides less overhead in creating a thread than creating a process. Next is scalability. Scalability, we can think in terms of multiprocessor. If a system is having multiple processes on it and it can execute more than one process at a time, then having a process with a single thread will have to make the other processes wait for some work for it to come, because only one process out of the remaining all the processes will be given job of executing the task. Whereas if it is a multi-threaded application, then each thread can be allocated to one processor on the system, and hence the task can be simultaneously done. Like for example, as we spoke about the word processor, the reading of the text can be done using one processor, spell checking can be taken care by another processor, processing or formatting the text can be done by another processor. So in this way, different threads can be allocated to different processors on the system so that they execute simultaneously and we get better execution or faster execution. That is how your modern systems are faster than compared to the older ones. User threads and kernel threads. Now I said that there are threads, but threads are of two types, user threads and kernel threads. The threads that are created by an application are all user threads, and the threads that are of the kernel or the operating system are called kernel threads. User threads are managed by the user level thread libraries, and the three primary thread libraries are POSIX pthreads, Windows threads, and Java threads. You all must have already learned about Java threads and created Java threads in your Java programming language. We also have similar threads for Windows and pthreads for Unix. Kernel threads supported by the kernel. So these threads are virtually any of the modern operating systems, all are multi-threaded, and examples are Windows, Solaris, Unix, Linux, 264 Unix, then Mac OS X1. All these are the different types of kernel. Next, we will be studying the multi-threading models. There are three types of multi-threading models. What is this multi-threading models? Multi-threading models means the relation between the user thread and the kernel thread. The user thread and kernel thread relation can be many to one, one to one, and many to many. Let's understand many to one. Many to one means multiple user level threads are mapped to a single kernel level thread. So many user level threads and one kernel thread. That's why it is many to one. So many user level threads mapped to a single kernel thread. So what is the advantage or disadvantage of this? There is a disadvantage that if one of the thread calls a system blocking call, then all the other threads are also blocked, because the thread that is connected to the kernel calls a system blocking call, and all other threads also block because the kernel thread itself is blocked. So operating systems like Solaris Green Threads, GNU Portable Threads are the ones which are using this type of a. This one is one-to-one. One-to-one is very clear that one user level thread is mapped to a kernel level thread. So every user thread is having its own dedicated kernel level thread. So this achieves a concurrency. It provides more concurrency, more number of processes or more number of threads in that process can execute simultaneously. But the problem here is that if we have n number of threads and we go on creating threads, then the CPU utilization will get little burdened. It will get overridden. So that's why we should always try and limit the number of threads that are created, because n number of user threads and n number of kernel threads, then it will happen so that the threads will not get proper CPU attention to execute any of these processes. So that's why we should always take care that the number of threads that are created in a one-to-one model is always restricted. Examples of operating systems that have these kind of thread support is Windows, Linux, Solaris 9, and later operating many-to-many model. The name itself tells that there are many user level threads which are bound to kernel threads, many or equal number of kernel threads. So allows many user level threads to be mapped to many kernel level threads. So this allows the operating system to create enough kernel threads. So Solaris prior to version 9 Windows and the thread fiber package are examples of this model. So in this case, the thread every user level thread is mapped to same number, equal number or lesser kernel level threads. Another version of this multi-threading model, two-level model. In a two-level model, there is same multiple user threads bound to multiple equal or lesser kernel level threads, but the only thing is that the thread is bound to the kernel thread. The user thread is bound to a kernel thread. Examples of this kind of an multi-threading model is IRIX, HPUX, Tro64 Unix, Solaris 8 and earlier. Threading issues. We have the following threading issues. First one, fork and exe system calls. Fork and exe. Fork is to create a child process and exe is to begin execution of the child process. So we'll see what was the issues we have when we are having a multi-threaded environment. Next is cancellation. So if any thread wants to cancel execution of the entire process, how this is going to get executed is what we will be seeing in cancellation. Signal handling is if operating system or if the process itself has requested something and there is an signal by the operating system to the process, how this signal has to be handled, by which thread it should be handled, which thread it should be given to, the signal should be given to which thread is what is the issues that we are handling in signal handling. Next we have thread pools. The thread pools means we create threads and we keep it ready for usage. And then next we have thread specific data and scheduler activations. So these are what are the threading issues that we need to take care when using a multi-threaded. First one, semantic of fork and exe. Now fork is used to create a child process. Now if you have a multi-threaded application and this process is having supposing 4 to 10 threads running in it, then if one of the thread makes a fork, means it calls the fork system call, in that case this process has to create a child process. Now the question is, should it create a child process with a single thread? That means the thread which called the fork, should that thread be duplicated or should all the 4 to 10 threads be duplicated? This question, there is two versions of fork that are there in some of the Unix operating system to resolve this. So if you call the fork which is creating a duplicate of the child process, then it directly creates a child duplicated thread process. Whereas if you call the second version of fork wherein it duplicates the entire process, so duplicating the entire process means duplicating all the child threads that are present in that process. So which one to use is a question. Before that, let's understand exe. What is exe? Exe means if the child process is created, when it should start execution is decided by exe system call. So when you make a exe, that time only the child process will begin its execution. So once you make an exe, the parent process and the child process both start executing and they go on their separate ways of execution. So that is what is the task of an exe. Now the question remains is which fork to call, whether single thread execution duplication fork should be called, or entire process duplication fork should be called. The question depends on when you're going to make the exe call. If you are going to make the exe call immediately, then there is no point in duplicating all the threads. It is better to call the fork with a same thread duplication child process, creation of the same process, duplication of the process for a single thread that called that fork should be used. Whereas if you are going to call the exe later, then you can call the fork version which duplicates all the threads of the process. Thread cancellation. So terminating a thread before it has finished is what is a thread cancellation. So that means the thread was executing. Take for example that you are using again a word processor and you are typing the text, and then during that time it is also checking for the grammar, and there are grammar corrections to be done. So the thread is waiting for you to do the corrections, but you stop the document or you close the document. So that closing will close all the threads in the process. Now here we are talking about when one thread makes a system blocking call. That means it is going to terminate that process, or it is going to only call the cancellation for one thread. So whether it is going to call for one thread or it is going to call for all threads, if it is going to call a close for itself, then there is no question, the others will execute. But if one thread is making a call to stop all the threads, to cancel the execution of all the threads, so in that case there are two approaches for cancelling the threads. One is asynchronous cancellation, in which it terminates the target thread immediately. So here if you see, asynchronous cancellation terminates the target thread immediately. So if there is 5 threads in the process, one thread makes a asynchronous cancellation, then all the 4 threads, the remaining threads which are executing, will also get terminated. Now what is the problem with this? The problem with this cancellation is that if the other threads have made a request for a resource, or if they are holding the resource, then those resources should be returned back to the operating system. So this particular call does not give space for other threads to release the resources, so that the threads release the resource and close in a normal fashion. So this will just abort the running resource threads, and hence the resources that are allocated to those threads will not be given back to the operating system in a proper fashion. So that problem can be solved with deferred cancellation. In deferred cancellation, the target thread, the remaining 4 threads which have to be cancelled, they don't cancel immediately. They don't cancel because of first thread calling a cancellation. The first thread makes a cancellation call and it closes. This cancellation keeps a flag ready to indicate for the other threads that they have to cancel their execution. So these threads, the remaining 4 threads, periodically check whether this flag is set for cancellation. If the flag is set for cancellation, they normally close or give all the resources back to the operating system and close in a proper fashion, so that none of the resources are in trouble. So that is how a deferred does not only depend on whether it is asynchronous or synchronous call. It is also dependent on whether the thread has enabled or disabled the thread cancellation state. So here in this table we see that there is a mode, thread mode, then there is a state, and then there is a type. So here if the thread is in off mode and it has disabled thread cancellation, then there is no issue because it is in off mode and it will not have any problem. It will get cancelled. Whereas in a deferred mode, if the state is enabled, then the deferred cancellation will work for this. But if it is deferred and if it is disabled, the state is disabled, then the thread cancellation will not occur until unless it enables this state. Next is asynchronous. In asynchronous, if it is state is enabled, then asynchronous calls will cancel the thread. But if it is disabled, the state is disabled, then the asynchronous cancellation call will not happen until unless it doesn't enable the cancellation state. So again, the cancellation is dependent on the state of the thread, whether it is disabled, thread cancellation is disabled, or it is enabled. So by default, it is the state is always it's always deferred. Default type will always be deferred, and if you wish, you can have an asynchronous type. So cancellation occurs only when thread reaches cancellation point, and for that you have in pthreads we have a method called as test cancel, and that will make a cleanup. We'll call the cleanup handler to give away all the resources back to the operating system and gracefully cancel the thread execution. So on Linux system, thread cancellation is handled through signals. Signals are used in Unix systems to notify a process that an event has occurred. So a signal handler is used to process signals, and signal is generated by an event. This event can be like a keyboard event or a mouse event, or it can be like an interrupt occurred or anything like that. So these signals are generated by an event, and signal is delivered to a process. Remember that signals are delivered to process, not to the threads. So the process has to decide to which thread this signal has to be given to. So signal is handled by one or two signal handlers. So it can be default or it can be user defined. So every signal has default handler that kernel runs when handling signal, and user defined signal handlers can override the default signal handler. For single threaded, signal is delivered to the process, so that particular signal. But if it is a multi-threaded environment, then whom this signal should be delivered to? Should the signal be delivered to the thread to which the signal applies? How do you decide which thread is that? Second one is deliver the signal to every thread in the process. Next option is deliver the signal to certain threads in the process. And last is assign a specific thread. Create a specific thread, receives all the signals and handles the signals. So next is thread pool. Time required to create threads is what is the most important aspect here. We have to give some time for creating the threads. So if you don't want that there is some time wasted in creating a thread when you require a thread, what you can do is you can have a pool of thread created, means create a set of threads, create some whatever threads that you require. Supposing you usually use you can say average number of threads that are required by the process, you create that many threads and keep it in a thread pool, and then whenever you require you can just pull up one thread and assign it the work that you want to assign it, and then when it finishes execution of that work, the thread goes back and sits in the thread pool for its turn to again service the request. So what is the advantage of this? The advantage of this is you don't create unlimited threads. If you create unlimited threads, you may exhaust the operating system resources like CPU time and memory. So solution is to create thread pools. Create a set of threads and keep it in a thread. Creating thread pools. The benefits are servicing a request with an existing thread is usually faster than waiting for creating a new thread. So the time that is wasted in creating a new thread, every time when you request, when you require some task to be done, that amount of time is saved. So it's better to have a thread pool, pick up a thread and start execution. If there are no threads, then only you need to wait. Otherwise, you need not need to wait for the task to be done. Second advantage is that a thread pool limits the number of threads that can exist at any point. So this is particularly important on systems that cannot support a large number of concurrent threads. So that is the benefits of having thread specific data. Now we have seen that threads have specific data and they have shared data. Sometimes the shared data, it is better to have a copy of it in a thread with the thread. So there we create thread specific data. Now threads belong to a process that share the same data, that is the data is shared between all the threads that are available, but we can have some data like it can be a session data or something which is related to a particular session. It can be related to the process, but you can have it as a thread specific data also. So the next threading issue is the scheduler activation. This scheduler activation is required in the threading model where it is many-to-many and two-level thread models. Why? Because there are multiple user threads that are mapped to the kernel threads. So for this mapping, we require a lightweight process, which is called as a virtual CPU, that is managing the bonding between the kernel level thread and the user level thread. So this helps in making a communication between the kernel level threads and the user level threads. So it is an intermediate data structure between the kernel threads and the user threads. So it appears to be a virtual processor. This is a virtual processor that is used to schedule user threads to run with help of the kernel threads. So each lightweight process attached to a kernel thread helps to run a user thread. So how many such LWPs you will require? It depends on whether the system is a single processor system. If it is a single processor system, a single kernel thread can run at a time, and hence there is only one LWP required, because any number of user threads you have, there is a single kernel thread, because more than one kernel thread is meaningless in a single processor system. Whereas if it is a multiprocessor system, then depends on the number of applications and the number of IO bond processes and CPU bond processes that are running. Based on that, you all will have to see how many LWPs are required. So you need to keep a balance, and you need to keep based on how many currently are the active threads that are running. So you can have, like for example, if there are 5 IO bond processes, then you can have 3 LWPs or 4 LWPs, wherein 4 simultaneously processes are running and one thread is waiting for an LWP to be free, and that's how you all can manage this. So scheduler activation here is required for providing a communication mechanism between the kernel threads and the user threads. So any signals that are coming to the kernel threads, they have to be provided to the user threads, and that is provided using the upcalls. And for this, there is an upcall handler that is taking care of this communication. So this communication allows an application to maintain the correct number of kernel threads that are required. So this is how we solve the threading issues. This threading chapter, we have finished unit 2 now. Next, we will start with unit 3. Thank you.